Imagine for a moment that every book ever written, every conversation ever recorded, and every photograph ever snapped was suddenly poured into a single, colossal digital reservoir. You are looking at a fraction of the raw material currently fueling the most significant technological pivot in human history. Research shows that leading large language models are now being trained on datasets exceeding 15 trillion tokens, a staggering volume of information that effectively maps the collective output of our species. This isn't just a database, it is a mirrorscape of human thought, logic, and creativity, compressed into a silicon architecture that is rapidly reshaping how we solve problems. Experts predict that within the next decade, this invisible engine will move beyond simple text generation to become the primary architect of our daily reality. We are witnessing a shift where the tools we build are beginning to anticipate our needs, diagnose our illnesses, and accelerate scientific discovery at a pace that previously took centuries. This is not science fiction, it is the logical conclusion of a decade of relentless progress in machine learning. Engineers have developed systems that don't just calculate, they interpret, synthesize, and iterate, turning the chaotic noise of the internet into structured, actionable intelligence. Data suggests that the influence of these models will soon be as foundational as electricity. Just as the power grid once electrified our homes and industries, these neural networks are now electrifying our information economy. They are the silent partners in our research labs, our creative studios, and our classrooms, quietly rewriting the rules of what is possible. But how does a machine actually learn to think? How do we translate the messy, subjective nature of human existence into the cold, precise language of mathematics? To understand the trajectory of our future, we must first pull back the curtain on the mechanics of the machine itself. Before we can grasp how these models will alter the fabric of our lives, we need to look beneath the surface at the complex, mathematical forge where intelligence is actually manufactured. That mathematical forge wasn't built overnight. If we trace the lineage of modern intelligence, we find ourselves stepping back into an era of rigid logic, where every outcome was tethered to a pre-written instruction. If a situation fell outside the parameters of the code, the system simply faltered. It was precise, yes, but it was fundamentally brittle, unable to cope with the nuance of the real world. But the complexity of tasks like language translation or visual recognition proved far too vast for manual rule writing. Research shows that, as we moved into the late 20th century, the limitations of these rigid structures became a bottleneck for innovation. We were trying to teach machines to think by giving them a map, rather than teaching them how to navigate the terrain themselves. This transition from explicit programming to machine learning fundamentally altered the relationship between human and machine. Instead of defining the logic, we began feeding systems vast, diverse datasets, allowing them to identify correlations that no human programmer could have intuitively mapped out. By stacking layers of artificial neurons inspired, however loosely, by the biological structure of the human brain, we moved toward architectures capable of hierarchical abstraction. These neural networks don't just process data, they decompose it, finding simple features in the lower layers and assembling them into complex concepts as the information rises through the architecture. It was a radical departure from the punch cards of the past. Yet, this newfound capability created a new set of challenges. As these networks grew deeper and more intricate, they became increasingly opaque, turning into black boxes where the decision-making process was hidden behind millions of weighted connections. Now that we have established this foundation of neural complexity, we must examine the specific fuel that powers these engines, because without the massive, messy influx of global data, these intricate architectures would remain nothing more than empty, silent shells. If these neural architectures are the skeletal framework of artificial intelligence, then data is the biological tissue that gives them substance. We aren't just feeding these models raw text or pixels, We are providing the statistical patterns that define our reality. Every image, sentence, and line of code acts as a teacher, guiding the model toward a more nuanced understanding of the world. You can think of these as millions, sometimes trillions, of microscopic knobs that dictate how information flows through the network. The model guesses, fails, and then encounters the most critical component of the entire process, the loss function. This mathematical gauge measures the distance between the model's incorrect prediction and the actual truth. Once this error is calculated, the model undergoes a process called backpropagation. Research shows that this is where the true learning occurs. It is a grueling, iterative cycle of trial and error performed at lightning speed. Data suggests that this process requires immense computational power because the model must repeat this cycle billions of times. With each iteration, the weights shift, the connections refine, and the black box begins to crystallize into a functional map of human knowledge. By the time the training concludes, the model has effectively encoded the statistical regularities of our collective output into its internal structure. However, even with the most sophisticated optimization, the model is still inherently constrained by the quality of the information it consumes. As we look at how these weights eventually stabilize, we have to ask ourselves what happens when the model stops learning from the world as it is and begins to mirror the biases inherent in the very data we fed it. Understanding how these systems generalize this knowledge beyond their training sets is the next great frontier in our journey. Stepping out of the theoretical constraints of the data center, we arrive at the most vital phase of the life cycle, the moment these abstracted mathematical weights translate into tangible utility. It is one thing to observe a model converge on a dataset. It is quite another to witness it navigating the chaotic, unpredictable reality of our daily lives. Consider the medical field, where diagnostic tools are no longer just repositories of static knowledge. Today, trained models act as a second pair of eyes for radiologists, scanning thousands of high-resolution images in seconds to flag anomalies that might escape human fatigue. This shift extends into the creative industries, where generative architectures are acting as a catalyst for human imagination. Writers, designers, and musicians are utilizing these models as collaborative partners, iterating on concepts at a velocity that was unimaginable just a decade ago. It is a fundamental shift in the creative process, moving from the blank page to a state of constant, fluid refinement. Even in the mundane rhythm of our daily productivity, the impact is profound. From the predictive text that anticipates our intent to the smart scheduling assistants that manage our cognitive load, these models are becoming an invisible infrastructure of modern life. To recap our journey, we have seen how raw information is transformed through massive parallel computation, how the delicate process of fine-tuning establishes behavioral boundaries, and how the stability of these systems relies entirely on the quality of their initial input. We have transitioned from the abstract mathematics of loss functions to the concrete reality of human-centric application. Looking ahead, the evolution of these systems will likely move toward greater transparency and efficiency. The goal is no longer just larger models, but smarter, more accountable ones that respect the nuances of human context. As we integrate these tools deeper into our societal fabric, the responsibility lies with us to determine how they serve our collective goals. If you found this exploration of technology fascinating, please consider subscribing to the channel for more deep dives into the mechanics of the digital world.